Welcome to the course on Python for data analytics, machine learning and generative AI. In this session, we will focus on statistics, which forms the backbone of data science and machine learning. By the end of this session, you should be comfortable applying statistical concepts using Python and interpreting results correctly. In this session, we will move beyond formulas and focus on how hypothesis testing is actually implemented in practice using Python. In real life, we usually don't have access to the entire population. So, we rely on small samples to make decisions. This is where statistical inference becomes powerful. It helps us bridge what we know from the sample to what we assume about the population. Hypothesis testing follows a standard and universal process, and mastering it makes your analysis reliable and repeatable. The first step is to clearly define the null hypothesis and alternate hypothesis. Next, we choose a significant level, often denoted by alpha, which sets the threshold for decision making. Then we collect and analyze data, calculate the test statistics, and determine the p-value. Finally, we make the decision, either reject the null hypothesis or fail to reject it, based on evidence from the data. The first step in hypothesis testing is defining what you want to test using two competing statements. The null hypothesis, written as H0, represents the default assumption or the current claim. The alternate hypothesis, written as H1 or HA, represents what we suspect might be the true instead. Once we have the p-value, we compare it directly with our chosen significant level alpha. If the p-value is less than alpha, we reject the null hypothesis. If the p-value is greater than alpha, we fail to reject the null hypothesis. Hypothesis testing decisions are not perfect, and errors can occur in real-world situations. A typo error happens when we reject the null hypothesis even though it is actually true. This is called a false positive, and its probability is controlled by alpha. A type 2 error happens when we fail to reject the null hypothesis, even though it is false. It is called a false negative, and it is linked to the power of the test. The primary goal of hypothesis testing is statistical inference. We use sample data to make conclusions about a larger population. Parametric tests are powerful but relies heavily on assumptions. Non-parametric tests offer flexibility when those assumptions do not hold. Traditional parametric tests assume data follows a specific shape, usually normal. When these assumptions are met, results are efficient and precise. Non-parametric tests make fewer assumptions about data structures. They are especially useful when data quality is uncertain. Parametric tests require strict adherence to several assumptions. These include normality, equal variances, independence, and sufficient sample size. Violating any of these conditions weakens the reliability of results. This checklist helps us evaluate whether parametric testing is appropriate. Small samples may not reflect normal population behavior. Skewed data and outlier distort means and variances. Ordinal data also limits the use of traditional parametric tests. Non-parametric tests do not depend on specific distributional assumptions. They work well with ordinal data, skewed distributions, and small samples. These methods rely on ranks or signs rather than raw values. As a result, they provide stable inferences in real-world settings. Let us see what is t-test, which are used when we compare means. There are three common variations: the one sample t-test, the independent two sample t-test, and the paired sample t-test. The one sample t-test checks whether a single group mean is significantly different from a fixed constant or benchmark value. The independent two sample t-test compares the means of two separate groups such as treatment group versus a control group. Finally, the paired sample t-test compares two measurements from the same subject, like before and after, by analyzing the shift between mean A and mean B. The goal is to determine whether the difference between these group means is statistically significant or simply due to random variation. First, we will learn how to check assumptions required for hypothesis testing using Python. Before applying any statistical test such as t-test or ANOVA, it is very important to verify whether the data satisfies certain assumptions. First, we import the required libraries. NumPy is used for numerical operations, Pandas for data handling, Matplotlib for visualization, and SciPy-Stats module for statistical test. Next, we define several data sets. The variable sample represents a single sample of observation. The variables group 1, group 2 and group 3 represent different groups used in comparative tests like ANOVA. The before and after data sets are typically used for paired test. Finally, a small matrix named data is created, which may be used for categorical analysis. Before performing hypothesis testing, we must check two major assumptions: normality and homogeneity of variance. To check whether the data follows a normal distribution, we use the Shapiro-Wilk test. A function named check_normality is defined. Inside this function, the Shapiro test is applied to the sample and the p-value is printed. If the p-value is greater than 0.05, we conclude that the data is normally distributed. In this case, the Shapiro p-value is approximately 0.96, which is greater than 0.05. So we conclude that the sample data follows normal distribution. Next, we visually inspect normality using a histogram. The histogram shows the distribution of the sample values. We then calculate the mean and standard deviation of the data. Using these values, a normal probability density curve is overlaid on the histogram. If the histogram bars align closely with the normal curve, it supports the assumptions of normality. Another graphical method for checking normality is the QQ plot. In this plot, observed values are compared against theoretical normal values. If the points fall close to the diagonal line, the data can be considered normally distributed. In our case, the points closely follow the straight line, confirming normality. Homogeneity of variance, also called homoscedasticity, refers to the assumption that different groups being compared have approximately equal variance on the dependent variable. Imagine you are comparing three groups of students based on their exam marks. Group A, B and C falls between 60 to 80. Here, all the groups have a similar spread of scores. This is homogeneity of variance. If group A has values between 70 to 75, B between 40 to 95, and C falls between 65 to 80. Here, one group is very consistent, another group is all over the place. The spread is not similar. This situation is called heterogeneity of variance or heteroscedasticity. Now we check the assumption of equal variance using Levene's test. Now we check the assumption of equal variances using Levene's test. A function called check_homogeneity is defined. This function takes multiple groups as input and calculates the Levene test p-value. If the p-value is greater than 0.05, we conclude that the variances are equal across groups. Here, the Levene p-value is 1, which clearly indicates that the variances are equal. We will now learn how to perform hypothesis testing in Python using different types of data. First, we will cover one sample t-test. We will cover one sample t-test, independent two sample test, paired sample test. For each test, we will first check assumptions and then automatically decide whether to use a parametric or non-parametric statistical test. Let us begin with the one sample t-test. The objective of a one sample test is to check whether the sample means differs from a known population mean. The function one_sample_test starts by checking whether the data is normally distributed using the Shapiro-Wilk test. Since the Shapiro p-value is greater than 0.05, the data is considered normally distributed. Because the normality assumption is satisfied, the code applies a one sample t-test. If the data were not normal, the Wilcoxon signed rank test would be used instead. Here, the null hypothesis is the sample mean is equal to the population mean, mu is equal to 25. The sample mean is not equal to the population mean is the alternative hypothesis. The p-value obtained is much smaller than 0.05, which indicates strong evidence against the null hypothesis. Hence, we conclude that the sample means differ significantly from the population mean. Next, we perform an independent two sample test. This test is used to compare the means of two independent groups, such as two different customer groups or two different classes. Normality is checked separately for group 1 and group 2 using the Shapiro test. Homogeneity of variance is checked using Levene's test. Since both groups are normally distributed and variances are equal, all assumptions for a parametric test are satisfied. If any assumption has failed, the Mann-Whitney U-test would have been selected. The mean of the two groups are equal, mu1 is equal to mu2 becomes the null hypothesis. And the alternate hypothesis is the means of the two groups are not equal. The p-value is less than 0.05, indicating a statistically significant difference. Hence, we can conclude here that there is a significant difference between the two group means. Finally, we'll perform a paired sample test. This test is used when measurements are taken before and after an intervention on the same subjects. The difference between the before and after values is calculated. Normality of these differences is checked using Shapiro test. Since the p-value is greater than 0, the differences are normally distributed. Because the normality assumption holds, a paired t-test is applied. If the differences were not normal, the Wilcoxon signed rank test would be used. Here, the null hypothesis is there is no mean difference between the before and after measurements. And the alternate hypothesis tells us there is a mean difference between the before and after measurements. Here, the p-value is less than 0.05, which shows there is a strong statistical evidence. Hence, we conclude the intervention has caused a significant change between the before and after measurements. When we need to compare more than two groups, simple t-tests are no longer appropriate. Instead, we use ANOVA-based methods. Let us begin with one-way ANOVA. We compare three or more independent groups. There is only one independent variable and the dependent variable is numerical. First, the code checks normality of each group using Shapiro test, homogeneity of variance using Levene's test. Since all groups are normally distributed and variances are equal, the assumptions are satisfied. Because the assumptions hold, a parametric one-way ANOVA is applied. If assumptions has failed, the Kruskal Wallis test would be selected instead. Here the null hypothesis is all group means are equal, mu1 is equal to mu2 is equal to mu3. And the alternate hypothesis is at least one group mean is different. The p-value is less than 0.05, which indicating a statistically significant result. We conclude that there is a significant difference among the group means. Next, we examine two-way ANOVA. Two-way ANOVA is used when there are two independent variables called factors. We want to test individual effects and their interaction effects. In this example, score is the dependent variable, method and gender are independent variables. The model evaluates the effect of teaching method, effect of gender, and the interaction between method and gender. The method effect is significant, the gender effect is significant, and the interaction effect is not significant in the result. Hence, we conclude here both the factors independently influence scores, but they do not interact. Now, let us look at repeated measures ANOVA. This test is used when the same subjects are measured multiple times. Measurements are taken at different time points or conditions. Each subject is measured as T1, T2 and T3. The test evaluates whether mean scores differ across time. The p-value is much less than 0.05, indicating strong significance. Hence, we conclude there is a significant change in scores over time. So far, we worked with numerical data. Now we move to categorical variables. This test checks whether two categorical variables are associated. The null hypothesis here is the two variables are independent, and the alternate hypothesis is the two variables are associated. The p-value is greater than 0.05 here, and hence we conclude that there is no significant association between the variables. Let's now see chi-square goodness of fit test. This test checks whether observed frequencies match expected frequencies. Observed and expected counts are compared across categories. Since the p-value is greater than 0.05, we conclude that the observed distribution fits the expected distribution. Finally, here we will discuss the Z-test, which is large sample mean test, which has been used when sample size is large and the population variance is known or approximated. The one sample Z-test is the test that checks whether the sample mean differs from a known population mean. Here, the p-value is equal to 1.0. Hence, we conclude there is no significant difference from the population mean. Let's now see what is two-sample Z-test. This test compares the means of two large independent samples. The p-value is very small, indicating strong evidence. Hence, we conclude there is a significant difference between the two group means. So, let us summarize. Normality checks guide the choice between parametric and non-parametric test. One sample test compares a sample mean with a known value. Independent test compares two unrelated groups. Paired test compares the measurements taken on the same subjects. ANOVA is used for comparing multiple means. And two-way ANOVA evaluates factors and interactions. Repeated measures ANOVA handles repeated observations. Chi-square test analyze categorical relationships. Z-tests are applied to large samples. Thank you.